So, good evening, everyone. This is your seventh week related to structural analysis course. This is your seventh problem solving session wherein we will try to solve the problems which we have covered in the current week. And this week we have started with indeterminate structures, and in indeterminate structures we have seen how the force method and the stiffness method are introduced to solve any problem related to indeterminate structures. So let me share my screen first, then we will discuss in details all the problems related to indeterminate structures that you have covered in the week number 7. I hope the screen will be visible to everyone. So let's start the session. So this session is a makeup session for the week number 7, which is a regular held class in Saturdays. But due to some unforeseen circumstances, this class got scheduled to Tuesday. So we will be covering whatever you covered in the week number 7. So in week number 7, you started with indeterminate structures. So introducing myself, my name is Pranav Mahajan. I am a research scholar in Department of Civil Engineering from IIT Madras. So till week number 6, what you have covered? You have started with solving the problems related to determinate structures. Now we are moving to indeterminate structures. So this whole course is divided into two parts. First half is now completed, in which you have seen that the first half covers the determinate structures, wherein we have solved the problems related to trusses, beams, and frames. So we started it as a building foundation by first defining how the shear force and the bending moment behavior varies along the different points of the beam section. Then we have seen that when you have a truss, then how you can determine the different forces using method of joints as well as method of sections wherever it is applicable, depending upon the complexity of the problem. From trusses, we have moved to beams and frames. In beams and frames, we have seen different methods to determine the slope and deflections at different points. We have seen how the moment area method can be utilized to determine slope and deflection. We have also seen conjugate beam method, in which we have seen how we can determine the slope and deflection by converting your real beam into conjugate beam and then determining the force and shear force and the bending moments, which will give you the slope and deflections of the real beam. Also, in certain cases, we have seen unit load method. Wherever it is applicable, we have applied unit load method, and we have seen how you can determine the displacement and moment and slope using that unit load method. After that, we have seen the impact of moving loads on the beams, or you can say bridges, or any structure in which moving load is about to occur. So in that, if we have required to calculate maximum shear force and maximum bending moment at any section, or if you are required to calculate the reaction forces due to the moving load, we have seen them utilizing the principle of influence line diagram, wherein Mueller-Breslau principle is required to be valid, and then we have determined the different components that are required to analyze the structure. Now, this is your first half of the course that you have covered. Now, your second half moves into indeterminate structures. So your indeterminate structures will work same as you have covered the determinate structures. Like you will start with beams, frames, and few problems related to trusses. But in this, different methods will come into picture. You will be solving the problems related to method of consistent deformation, moment distribution method, slope deflection method. Okay, so talking about this statically indeterminate structure, so how can we determine that whether a structure is determinate and indeterminate? it depends upon the degree of indeterminacy. When your reactions in the structure are more than the available equations that are required to solve the structure, then the structure is considered to be indeterminate. Okay, that means if the total number of reactions are more than the total number of equilibrium equations to solve the problem, then the structure is considered to be indeterminate. Now, in this week, we will see how the force method and stiffness method is used to solve the problems related to indeterminate structures. So starting with the basics, we will see first what is force and what is stiffness method. Okay, so we have an infinite number of systems which satisfy the equilibrium equations. Okay, but among them, there is only one system that satisfies the boundary conditions also. So that means every system not only have to satisfy the equilibrium equations, but it also needs to satisfy the boundary conditions. So to solve such a system wherein boundary conditions are also required to be satisfied, we use force method, or you can say flexibility method, or displacement method, which is also known as stiffness method. Now talking about force method, what we will do in this? In this, we will take the redundant forces, or you can say additional force, which are available in addition to the available equilibrium equation in the structures. Okay, so that forces are considered as first unknowns. Like if you have a prop cantilever in which you will be having a degree of indeterminacy equal to 1, in that you will consider the prop reaction to be a redundant force, and then you will try to solve the problem. Now let's see further what is written. So first we will take redundant forces as unknown, then additional equations are obtained by considering the displacement compatibility. That means now we have a propped cantilever in which at the propped end you will observe the displacement to be 0. So this will come as an compatibility equation for your structure, wherein you will try to make the displacement at the propped end to be equal to 0. How you will make it 0? We will see the steps involved in solving using force method. So what are the steps that are required for using force method? So first step involves determining the degree of static indeterminacy. So this is the basic steps that everyone should know, that whether the structure is of 1 degree, 2 degree, or 3 degree indeterminacy. Then we will select the redundant force or moment depending upon the type of the problem you are expected to solve. Okay, after selecting the redundant force and moment, the solution of the basic determinate structure under load is then calculated. So this is the first basic thing that you have to do. That now what you will do, you will remove the redundant force, and then you will find the displacement at the point where redundant force is applied. Okay, then in next step what you will do, you will find the solution of the determinate structure under redundant. Now you will remove all the external load, and then you will apply only the redundant force, and then you will see at that particular point how much displacement you are expecting only due to the redundant force. Now you will apply the compatibility equation. So for a prop cantilever, if we see the displacement equation, or the displacement at the propped end to be equal to 0, will become your compatibility equation. Okay, so after that determining the compatibility equation, you will take the unknowns and your unknown values will be automatically calculated. So this is the basic steps that are required to calculate any problem using force method. In another sense, you can say force method is a superposition method in which you first break down a structure into simpler values or simpler supports or simplest conditions, and then you will determine what are the values of slopes and displacement you are observing and at that particular point, and what should be the value it should be coming. That means, like if you are having hinge support and the roller support, so in that you are confirmed that displacement or deflection at the support should come out to be zero, so that becomes your compatibility equation for that particular structure. So you have to determine the compatibility equation, then only you will be able to solve the problem by breaking down into smaller steps. Okay, so this is the general overview of force method. We will see some problems related to that. And first of all, we will start with the finding of degree of static indeterminacy, which will brush up your concepts that you have covered in the first two lectures. Now, differentiating between the force or the flexibility method, or we can say the second method is displacement or stiffness method. So if I try to differentiate between them, what you will do in the force or flexibility method, you will first determine the degree of static indeterminacy. Then you will determine the number of redundant forces, like previously we have seen the whole procedure. After that, we will find the displacement in the basic statically determinate structure under load and redundant forces. So this is the two-step. The point number 3 is considered to be a two-step, in which you will first determine the displacement under load, removing all the redundant forces. Then what you will do, you will remove all the forces and then see the displacements due to only redundant force. After that, displacement are expressed in term of redundant using flexibility format, that you will see in the coming lectures, that how you can express the redundant forces in the flexibility format, and then you will apply the compatibility equations and find out the redundant values. So simple procedure. If you solve the problems, you will be able to understand. Don't go into the details of the language that is written in this. Problems are expected to solve when you understand the concepts. If your understanding of the concept is good, you can be able to solve the concept either by any method, either it is force method or displacement method, whatever is required or whatever is simpler to determine the unknowns in that particular problem. Whereas in the displacement method, which is also known as stiffness method, in this you will determine the degree of kinematic indeterminacy. So degree of kinematic indeterminacy is also known as degree of freedom. Okay. Then you will identify the unknown displacement whose number is equal to nk, or you can say n underscore k. Then what you will do, you will restrain the above displacement and find the forces in the basic kinematically determinate structures. Then forces are expressed in terms of displacement using the stiffness format. And finally, you will solve the equilibrium equation to find the displacement. Or in another sense, if you can say, this force or flexibility method is just an inverse of the stiffness method, in which what you will do, wherein you will not consider, if we start with the differentiating of them, you will first find that the static indeterminacy, which is the consideration of the forces. Whereas in stiffness method, you will first find the degree of kinematic indeterminacy, which will tell you how much structure is able to carry out the rotations and the displacement. So what you will do, you will restrain that displacement and then you will find the forces due to that displacement. Whereas in force method, what we will do, we will remove the restraints which are providing the displacements, and then we will determine the forces. Okay, so both are interrelated to each other, but the concept of them is somewhat in an inverse relationship between to each other. Okay, so this is the basic difference, or you can say basic method steps that you will follow to solve any problem using force and displacement method. Okay, so let's solve some basic problems first. First, you will solve the problem related to determining the static indeterminacy of any frame. So this is a frame in which you are having two bays. In this you can see that at base you are having one fixed support, one roller support. So this is your fixed support, this is your roller support, and this is your hinge support. Okay, and you have frame, and now you are expected to calculate the degree of static indeterminacy. So how you will do? So in this, in each and every point you will be having three reactions, 1, 2, and one moment. Okay, these three. Similarly, in each and every point you will be having three reactions, like this. So these are your unknowns that you are expected to calculate in these. Okay, so in every beam or frame you are expected to calculate the unknowns, which are shear as well as the displacement. So these are the unknowns in the members. Now talking about the unknowns at the support. So in the fixed support, so this is your fixed support, this is your roller support, and this is your hinge support. Now talking about number of unknowns in this, you can see that in the fixed support number of unknowns are 3, 2 are reactions, and 1 is rotation or movement. In case of roller, the number of unknown is 1, that is the only vertical reaction. In case of hinge, you will be having 2 reactions as your, what you can say, 2 reactions as your unknowns, and each frame element you will be having 3 number of unknowns. Okay, so now your total unknowns here will become, so here R equal to number of unknown reactions, and this will become equal to 3 plus 3 plus 3, 4 times 3, and now 3 for fixed support, 1 for roller support, 2 for hinge support, and this total accumulates to 18. Fine. Now what you will do? Number of available equations that will become 3 into n, that will be 3 into 3 equal to 9. Okay, now your degree of static indeterminacy is equal to number of unknown reactions minus number of available equations. So this will become, your ds will become equal to number of unknown reactions we have already calculated as 18. Number of unknown reaction available equations we have calculated to be 9. So your ds will come out as 9. Okay, so your degree of static indeterminacy in case of this type of frame will be 9. Okay. So now this is how you have to first determine the static indeterminacy in any structure. Then you have to proceed further to determine the redundant forces. Okay. Now talking about how you will determine the degree of, or you can say kinematic indeterminacy. So if you recall what is kinematic indeterminacy, it is the number of degree of freedom that are available in a structure. That means in how many ways a, a point in the structure can either displace from its original position or it can rotate in the means you can say vertical or in rotational frame. Okay. And we already know, since in case of fixed support, you have restraint in vertical, horizontal, as well as moment restraint is also there. So that support will be having degree of kinematic indeterminacy equal to 0, because that point can't move in any direction. Whereas if you see in case of hinge, you have restraint in vertical direction and horizontal direction, but in this case hinge you will be having moment which is free to auto. So in case of hinge, your degree of kinematic indeterminacy will become equal to 1. Now if I talk about roller, in roller there is only one reaction, that is vertical support. That means roller can move in either horizontal direction and they can have the rotation in that particular they can have rotation in that particular beam member. Okay. So that means in case of roller you will be having two kinematic indeterminacy. Okay. So if I talk about kinematic indeterminacy of this frame, so this frame you can see you will be having one fixed support, one hinge support, okay, and one point member that is there inside the structure. So for fixed, I already told you that degree of kinematic indeterminacy is equal to 0. For hinge, this can rotate in this direction. That means moment is available. So in case of hinge, your degree of kinematic indeterminacy will become equal to 1. Now if I talk about the joint between the vertical and the horizontal member, you can see in this horizontal and vertical reaction both are possible, and in addition to that you can also have rotation in this. So that means in this case your degree of kinematic indeterminacy will become equal to 3. Okay. So if I talk about the cumulative degree of kinematic indeterminacy, so that will become degree of kinematic indeterminacy, that will be equal to 0 plus 3 plus 1, and it will be equal to 4. Okay, fine. So this is how you are expected to calculate the kinematic indeterminacy. So if you know the kinematic indeterminacy, your next step is to utilize the stiffness method and then determine the displacement in the redundant structure you are expected to solve. Now, talking about another question, you have one more question in which you have to determine the degree of kinematic or kinematic indeterminacy. In this, the main important point that is available for you is this, that provided the structure is axially inextensible. That means your horizontal reaction in the structure at every point will be equal to 0. Fine. So this is the basic point you have to see, that whether axially inextensible is provided to you or not, or some any other conditions which will violate your basic concept, in which you can say, like, for roller support you will be having two reactions, horizontal and moment. Sorry, in case of roller support you will be having two degree of kinematic indeterminacy, due to one is axial force, or you can say horizontal force, and another is due to moment. But due to this condition, the structure is axially inextensible. Your reaction force will become equal to 0. So in that case, for the roller support, you will be having only 1 degree of kinematic indeterminacy, and that will be equal to 1. And that comes out only due to the moment force, not because of axial force or horizontal force, due to the provided condition in the question, or you can say in the journal structure also, where it is mentioned that your structure is axially inextensible. Fine. So similarly, like in this question, you are provided with two roller supports. So see there, you are having two roller support. So this is your roller support 1. This is your roller support 2. In this case, your dk should be equal to 2. But due to the presence of this axially inextensible condition, your dk will become equal to 1. Same thing will happen in this case also. Your dk is equal to 2, but due to the axial inextensible condition, your dk will become equal to 1. Now, if I talk about this internal support or internal hinge, in this you will be having one force due to shear, one force due to clockwise moment, and one due to anti-clockwise moment. So in this case, due to internal hinge, your degree of kinematic indeterminacy will come out to be 3. Okay. Now, if you try to sum up all of them, so for this case, your degree of kinematic indeterminacy will be 1 plus 3 plus 1, and that will be equal to 5. Okay. So understanding of how to determine the kinematic indeterminacy as well as the uh, degree of static indeterminacy is very important to solve any problem. Okay. Now, if I talk about if how you will solve the fault trusses. So fault trusses, it is very easy for you. You have degree of indeterminacy using the journal equation, that is m plus r minus 2j, where m is number of members and in this case your number of members are equal to 3. Okay. For triangle they are having 3 sides, so 3 number of members are there. Now if I talk about r, which is number of unknown reactions, so your number of unknown reactions in this case will become, you will be having here two hinge forces. I will show you here. So you will be having two hinge forces. This will be having 2. This will be having 2. How it is 2? One is vertical. Here also one is vertical. And one is horizontal. Fine. So in this case, your R will become 2 plus 2 equal to 4. Now if I talk about J, so J is number of joints in truss. So in this case, number of joints will be 3. Okay. Now if you find the degree of static indeterminacy, so your degree of, let me write with black. So your degree of static indeterminacy in this case will become equal to m plus r minus 2j, and that will become m is 3, 4 are reactions, minus 2 into j is 3, so that will become 4 and 3 7, and 3 into 2 6. So your indeterminacy will become 1. So that means you have a degree of static indeterminacy equal to 1. That means out of 2 hinges, if you convert one hinge into a roller support, then solve the problem. After that, you remove all the forces, and then you apply a unit load wherein you have removed the redundant, and then see how much forces you are observing in the truss. Based upon that, if you compare using compatibility equation, you will be able to determine the unknown force, or you can say redundant force, in the truss member, and that will help you in determining or solving the problem using force or flexibility method. Now let's move further. Again, you are having one question in which you are expected to determine static indeterminacy. Now I think you are now familiar with how to determine them. So see, this is your hinge support, this is your roller support, and these are your internal hinges. I will write it as internal hinge, internal hinge. In this case, your degree of static indeterminacy comes out to be 1, because only one reactions are there in the structure. In case of hinge, your degree of static indeterminacy is 2, because you are having two forces. One is vertical reaction and another is horizontal reactions. Okay. So your number of unknown reactions in this case equal to 1 due to roller and plus 2 due to hinge will be equal to 3. Now talking about number of available equations. So in this case, your number of available equations will be equal to number of equilibrium equations plus 1, in bracket I am writing, due to internal hinge 1 and plus 1, this is due to, I think I will write with some other color, that will be easy for you to understand. First 1 will come, this is due to internal hinge 1, plus 1 again will come, and it is due to internal hinge second. Fine. Okay, so your total number of available equations will become, so your number of available equations will become, so how many number of equilibrium equations are there? 3 plus 1 due to internal hinge 1 and plus 1 again due to internal hinge 2. That is total 5. Now if I talk about degree of static indeterminacy of the structure, so your degree of static indeterminacy, as I already told you, it is equal to number of unknown reactions minus number of available equations, and if I try to make it, what it will become? 3 are the number of available reactions. If I talk about number of available equations, it is 5. So your kinematic, your degree of static indeterminacy is coming out to be minus 2. Okay. So in this case, you have got the negative degree of static indeterminacy. Okay. Now in the same question, if you are expected to calculate the stability of the truss, so how you define the stability? So stability structure is said to be stable if degree of static indeterminacy is equal to or greater than 0. If it is greater than or if it is less than 0, the structure is considered to be unstable. Okay, so here, since degree of static indeterminacy is coming out to be equal to minus 2, so the truss is unstable. Now if we have to further classify that whether it is internally unstable or externally unstable, how we will define that? So if you see in the question, there are 3 unknown reactions. There are 3 unknown reactions externally. Fine. And you have 3 number of external equations. So that means your degree of static indeterminacy due to this will become equal to 3 minus 3 equal to 0. So your external indeterminacy is 0. Now talking about internal indeterminacy. So here number of additional equations number of available equations to solve the structure is 5. So your internal indeterminacy will become equal to 3 minus 5 equal to minus 2. So therefore the structure is, or the truss is internally unstable, because your internal static indeterminacy is equal to or is negative, whereas your external static indeterminacy is 0, that is just stable. Okay, so in this case it is just stable. Fine. Now let's move to another question. So this question is, how many redundancies are required to be removed to make the structure to be statically determinate? So number of redundancies, are, what you mean by redundancies? Number of unknowns. So your number of redundancy will be equal to degree of static indeterminacy of the structure. Okay, so in this case you are having one hinge. So this is your hinge. This is again you are having hinge. In this case your degree of static indeterminacy is 3. Here also your degree of static indeterminacy is equal to 3. Now if you calculate the total degree of static indeterminacy, or if I write not static indeterminacy, unknowns, I think R is better term to write here. Your R, that is number of reactions, are equal to 3. So here R, here it is 3. So your degree of static indeterminacy will become number of unknowns number of unknown reactions minus number of equilibrium equations that means your ds will be equal to, total you are having 3 plus 3 equal to 6 unknown reactions minus 3 number of available equations. So your degree of static indeterminacy will become equal to 3. That means 3 redundancies are required to be removed to make the structure as statically determinate. Fine. So if you so in case of hinge beam, your degree of static indeterminacy will always come out to be equal to 3. So that means he 3 Fitz beam is having the static indeterminacy of order 3, and when you will remove all the 3 forces, or you can say one hinge from the structure, then only the structure will become statically determinate. Fine. Now talking about next question, you're having one big frame. In this, it is mentioned, or additional condition that is provided to you is to ignore all the axial deformation of the members. Now, after ignoring all the axial deformations, how many free degree of freedoms that are available in the frame you have to calculate, and that will become your degree of kinematic indeterminacy. Okay. Now, if I talk about the large columns, axial deformations are absent. That means they can move in this direction. Horizontally, they can move. Okay. So let me mark them. So that means these are your unknowns that are available. And since all these joints are attached to each other, so amount of horizontal displacement that is observed on the first column, the same horizontal displacement will be observed in all the columns. So that means you don't have to consider the unknown value for all the columns to be separately. If you are taking for one column, that means you are taking the static indeterminacy to be for all the columns. So the best example to understand is, you will see if you apply a unit load in the beam, how the whole frame will move, because if you apply the unit load, the deflection at each and every point in the beam will be equal in the horizontal direction. So that's why if we consider only one beam, that means we are considering all the unknowns that are occurring in this whole structure. Now, talking about another thing that will be going to occur in this is the moment, because due to the application of these horizontal forces, you will also observe one moment at each and every point. Okay, so here, let me change this. Yeah, this is fine. So that means if you are applying horizontal force in that whole structure, you will observe rotations also in the members. So these rotations are not equal in each and every bay frame. Okay, so that means your rotations at each and every point will be unknown, and you have to determine the moment at each and every point of the section. So that means all the elements of these bay frame will observe unknown reactions due to the moment. So these are the values, or these are the directions of the reactions that you will observe as your unknowns, or you can say these are the independent coordinates that are available in that problem to act as an kinematic indeterminacy. Now, talking about the external indeterminacy, external kinematic indeterminacy, you are having one hinge and one roller support. So in this case, you already know that in case of hinge, that only one decay, or you can say one degree of kinematic indeterminacy is there, because this hinge is providing restraint in horizontal as well as in vertical direction. This hinge is able to deform in the moment. Okay, that's why in the case of hinge, you will observe the degree of kinematic indeterminacy to be equal to 1. Whereas in case of roller, you will observe the degree of kinematic indeterminacy to be equal to 2. That means you will be having, in case of roller, you will be having one horizontal deformation as well as rotation to occur, because a roller will provide only one reaction, that is one vertical reaction. In all the other direction, it is free to deform. So that's why in case of roller, the degree of kinematic indeterminacy is equal to 2. Now, if we add up all the values, you will be able to determine the degree of kinematic indeterminacy of the whole frame. Okay, So let me write in the next slide. So your degree of kinematic indeterminacy so this will be equal to, so at each frame, oh I think I am marked in the frame, it is at each corner. Let me try to move them. I think if it is possible I will move that. No, this is not possible, so let me remove them. I will again add them. Yeah, so these all moments will come at each joint, not at the center. So let me mark them at the joint, then it will be easy to understand. So yeah, at each joint you will observe one moment like this. So for every floor you are experiencing four unknowns due to moment. So these unknowns are for kinematic indeterminacy. So you are having five number of floors: one, two, three, 4, 5. So in 5 floors, 4 uh, values are there due to moment, plus due to the horizontal forces. How many values are there? 1, 2, 3, 4, 5. So 5 are due to horizontal forces. Not talking about due to external supports. So 1 will come due to hinge and 2 will come due to roller support. So that will contribute to as 20 plus 5 plus 3, and your total degree of kinematic indeterminacy accumulates to 28. Fine. So for the large frame, if you are expected to calculate degree of kinematic indeterminacy, so this is how you will calculate that. Okay. So now your next question is, you are available with one prop cantilever. So that means your, if the cantilever beam is propped, that means this structure is indeterminate. Okay, now you know the structure is indeterminate. So depending upon the complexity of problem, you can choose any of the method. You can choose either the force method, and you can choose either the stiffness method to solve the problem. So for the sake of understanding, we will start this session for using force method. So in this question, let me read the question first. So in the following statically indeterminate beam, consider the vertical point C as the redundant force. Now calculate the value of vertical displacement at point D1 with point load but without any restraint at C. So determine the value of D1. Consider the flagellal rigidity of the beam to be EI. So this is the pure problem for the force matrix or force method. So we will first write using force method. So using force method, the question is already telling you the steps to solve the problem, but in journal it is not available with you. So we will start with the basic things that we are expected to calculate. First, we will calculate degree of static indeterminacy. So in this case, you are having the number of unknown reactions. Let me write here with the red pen. So for hinge, your number of unknown reactions are 3. In case of this roller, or you can say prop support, in this your number of unknown reactions are 1. So your total available unknown values will be 3 plus 1 minus number of available equations, that will become equal to equilibrium equation, and that will contribute to, so if you calculate total degree of kinematic indeterminacy, it will come out as 1. That means now you have to choose, one reaction as redundant then remove it, and further calculate the displacement at point C. So point C is the one where redundant force is there. So we will consider the displacement at point C. Okay. Let me bring it a little bit down. Fine. Now what we will do, we will remove this and then solve the problem. So in this, now we are removing the redundant force, and then we are solving this problem as an cantilever beam subjected to a point load at the center. So now you are having the problem as cantilever beam subjected to point load. So this point load is equal to 10 unit. Okay. Let me write the value of support, that is A, B, and C. Now we will use the conjugate beam method, and then we will determine the value of displacement. So starting with the conjugate beam method, if you recall how it is done, so based upon the value of real beam, we will draw the bending moment diagram of the real beam, and then we will convert that bending moment diagram of real beam as the equivalent diagram for the conjugate beam. So let me draw here the conjugate beam in this case, then it will be easy for you to see that. So in case of conjugate beam, your free end will become fixed end, and your fixed end will become your free end. Okay, so this end will now become fixed, and your bending moment diagram of the real beam will become the loading diagram of the conjugate beam. So now this will become your loading diagram. So now I am making this as the loading diagram. Now what will be the value, maximum value of this loading diagram? Okay, if you try to calculate that, its maximum value will come out to be, since here it is 5 unit, here also it is 5 unit, so your moment will come out as 10 into 5 divided by EI, and that will be equal to 50 upon EI. Fine? Understood? Okay. So now, if you apply the principle of conjugate beam, so if you have to require the displacement at the free end, or you can say displacement at point C, you have to determine the moment of the this loading diagram or moment of the conjugate beam at the point C, and that will give you the deflection at the free end of the real beam. Okay, I think I am able to communicate to you that. So that means your moment at C of conjugate beam, let me move it a little bit down, of conjugate beam, that will be equal to deflection at free end C of the real beam. Fine? Understood? Now let's calculate the moment at the point C of the conjugate beam. So if let me mark it as D1. So in this case, first I will take the area of this bending moment diagram, that will become 1 by 2. The maximum value is 50 upon EI. And what is the distance? It is 5. So this is your area, and its moment author at 2 by 3 of 5 plus 5. It will come out as 5 plus 2 by 3 of 5, and that will become equal to, so this will be equal to 250 upon 2EI multiply with, the distance will be 25 divided by 3, and if you solve this, you will get the value of D1 as 3125 divided by 3EI. Fine. So this is the value of displacement that you will observe when prop support is not there in the cantilever beam with the uh, load of 10 unit applied at the center of the beam. Okay, now what we will do, let's see the next question. So next question is telling you, this is the continuation of the same previous question, and I will continue the solution also. In this, you have to calculate the vertical displacement D2 for just redundant force acting upwards but without point load. That means now you don't have to take this unit load. Okay. Now using the compatibility of displacement at joint C, calculate the value of reaction and consider the flexural rigidity of the beam to be equal to 1. Okay. So now I am continuing with the previous question only. We have calculated the value of D1, which is the deflection at the free end of the beam. Now what we will do, we will again use the concept of conjugate beam, and we will make the structure for this section. Let me draw it. So suppose this is your beam. So I am removing all the forces like 10 unit of external load that is applied on the structure. I am removing that. Now I will convert this beam into this. Now nothing is there in the section. You are having only the reaction support. Okay. Earlier you are not having any support at the free end. Now this reaction support is, suppose I am saying, to be equal to Cy, and this is your fixed end. So this is only your real beam only. Okay. And dimensions are same. These are 5 unit. These are 5 unit. Now what is told to you? You are told to convert this beam into the conjugate beam, and then you will determine the displacement at the support C, and then we will discuss further. Okay. Now convert this real beam into equivalent conjugate beam. So how you will do? So in this case, your free end will become fixed end. Now, as you have already seen, that your bending moment diagram of the real beam will become the loading diagram of the conjugate beam. So if I try to make the bending moment diagram of the real beam, so this is how it will look like. A linear variation along the length. Okay, this is how it will look. And if I talk about the loading, so the loading is almost linear. So the loading is linear along the length of the beam like this. and the maximum value of loading in this case will come out as cy into 10. So that means 10 cy upon ey is the maximum value. Fine. And it is having the same units or same dimensions as 5 units, 5 units. This is your support A, B, C. This is your A, B, and C. Fine. And this is your conjugate beam. Now, if I copy the same line, your moment at C of the conjugate beam will be equal to the deflection at the free end of the real beam. So this concept will remain same further also. Okay. So I will use the same concept again. See. Okay. So now I am writing it to be D2. Fine. So this D2 is the moment at C of the conjugate beam. Okay. So that will be equal to, first you will calculate the area of the bending moment diagram, that is 1 by 2 into maximum value is 10 upon 10 cy upon ei. Distance is total 10 multiply by the moment of the loading diagram, that will be 2 by 3 of 10. Fine. And this will become equal to minus, this will be negative, because if I am taking one as positive, another one will be negative, because one is in upward direction and another is in downward direction. Fine. You can take any one of them to be positive or negative. So your deflection at the point C will be coming out as the equal to minus 1000 divided cy upon ey. Now you will be using compatibility equation to solve the value of unknowns. So now using compatibility equation. So what do you mean by the compatibility? That you have to see how it will affect the structure. So I will first describe you that at joint C, due to roller support, displacement, or I will write vertical displacement, will be equal to 0. Therefore, your D1, which is the deflection without the reaction support, plus D2, which is the deflection at the joint C only due to reaction force, will become equal to 0. Now you will solve further. Your D1 you already know it to be 3125 divided by 3ei, and your D2 you have calculated it as 1000 cy divided by 3ei equal to 0. So if you solve further, it will become 3125 minus 1000 cy equal to 0, and that will give you the value of cy equal to 3.125 units. Fine. So this is how you will solve any problem related to force method. So that means now we have calculated the unknown additional redundant force using force method, and after knowing this redundant force, now we can solve the other unknown forces using the equilibrium equations that we have already discussed in the last 6 weeks of this course. Okay, now from the next week we will see the problems related to method of consistent deformations, and that will help you in solving the problem related to the addresses. Okay, so this week what we did, we started with analysis of statically undeterminate structures, and that is the start of your second part of this course, and this second part will continue further for all the statically indeterminate cases. So we started with how we can define the problems, or how we can define the degree of uh, static indeterminacy in beams, in truss, in frames, how we can determine kinematic indeterminacy in all these structures, because in case of indeterminate structures, how to determine the value of static indeterminacy and kinematic indeterminacy is the most important step to proceed further. Okay, so that we have understood by different examples that we have solved today. After that, we have seen one problem related to force method, in which we are provided with the top cantilever beam subjected to a point load at the middle of the section, and we have seen how to solve that problem. So what we did in that question, we started with finding out the static indeterminacy of the whole structure. So after finding out the static indeterminacy, we found that the static indeterminacy is coming out equal to 1. That means we have to remove one unknown forces from the whole structure to make the structure to be determinate one. Okay, so what we did, we remove one force, that is your prop cantilever, or you can say propped support from that section, and then we have analyzed that section using conjugate beam method, and we have determined the value of deflection at the free end, because we already know that deflection at free propped end of the cantilever beam is equal to 0, due to there is one vertical reaction at that support, because that compatibility equation only will help you to solve the whole problem. Now you have solved the value of statically determinate structure that you have obtained after removing the value of propped support, and you have determined the value of displacement at the free end. Now what you did, you again removed all the external forces, and you have applied one external reaction. And after applying one external reaction, whatever displacement you are observing at the point C, you will try to find out. Okay, so in our case, it is coming out to be equal to minus 1000 cy upon 3 ei. Okay, now you will use the compatibility equation to determine the value of cy, which is unknown in our case. So what we did, we have added the whole, both the deformation that we have observed, that is d1 plus d2 will become equal to 0, and if we have simplified further, we got the value of cy equal to 3.125 units. So this is how you will solve all the problems related to force method, and with increase in the value complexity of the structure, your all the calculation will become difficult to solve. That's why in the later stages you will see, you will not solve this problem. I am telling you not about this coming week. I am talking about the 12th week. That in 12th week you will see if there are number of redundant forces there in the structure, then you can't solve the problem directly applying the force method. You have to use flexibility matrix method. That matrix method is based upon this force method only, but you map up all the values that you will observe in different point of the structure, and then you will find out one matrix that you will say it to be a flexibility matrix, and then you will solve the value of unknowns that are there in the structures, and it will help you in understanding of this whole structure, not only for the basic beams, but in when the structures are very complex. In that condition, how you will be able to determine the value of unknown forces in the structures. So today's session we will wrap up today. If you have any doubt, you can ask, or then we will wrap up. And from next week, we will see some problems using the method of consistent deformations. Okay. So anyone have any doubt? So let's meet this Saturday. So this Saturday we will take the class on a regular time that we are considering every week. That is Saturday 6 to 8 p.m. And then we will solve the problem that you are currently seeing the NPTEL videos related to method of consistent deformation. So based upon the uh, lectures that you will see today, we will try to solve the problems related to that. So let's meet on Saturday. I hope you have liked this session. Okay. So enjoy your day. Thank you, everyone.